Hello guys and welcome back to my YouTube channel. In this video we're going to be talking about reactions with carboxylic acids and SOCl₂, so the formation of an acyl chloride. And then after that we're going to talk about hydrolysis of an acyl chloride, how you go from this to that and how you go from this to that. So starting with the first mechanism. The first step of every reaction ever is to find the nucleophile and find the electrophile. So I'm going to look for the most electronegative or electron-rich atom. So here my options are oxygens, sulfurs, or chlorines. When chlorine, so any halogen, already has one bond, it is very unlikely that the chlorine would take 2 electrons right now and go and attack something. So I'm going to veto the halogen. So I'm going to say, what about one of these oxygens? I could say, yes. It is actually very likely that one of these oxygens is going to react. In fact, if I consider its resonance structure, so drawing in all my lone pairs, going 2 over 2 up, what do I get? So I'm going to draw the resonance structure. I get an O minus because the electrons flowed towards this top oxygen. And then we get a double bond between the red oxygen and it's still attached to that proton, so it becomes positively charged. So now I see that, well, I have a nucleophilic atom. I have an atom with a negative charge. So who would this atom want to attack? Well, nucleophile means nucleus loving. So go to your other reagent and find an atom that is very delta plus. So on the SOCl₂, who's delta plus? Well, chlorines are electronegative. They're halogens. And oxygens are electronegative. That means all 3 atoms around the sulfur are pulling electron density towards themselves. So what does that mean for the sulfur? Well, it means the sulfur is very delta plus. So very electrophilic, meaning nucleophiles are very likely to attack it. So this oxygen is going to take one of its lone pairs, and it's going to go bada bing, attack the sulfur. Then would the leaving group just leave? Bada boom? Nope, not yet, because pi bonds are weaker than sigma bonds. So the first arrow would go 2 up, and one of the SO bonds would break. Draw an arrow, and we will draw our first intermediate. So draw in all the bonds that did not change. So we have the R to the carbon, double bonded to the red oxygen, which is still bonded to that hydrogen. It still has its lone pair and it's still positively charged. Now the other oxygen took one of its lone pairs, right? And it attacked, so a new bond was made to the sulfur. The sulfur still has 2 single bonds to the chlorine groups. And now it only has 1 bond to the other oxygen, and that oxygen is negatively charged. And I hope we see the trend here. So step 1 of this reaction was nucleophilic attack. Nucleophilic attack. Now step 2 is you get this intermediate where the oxygen is negatively charged. Intermediate. So now you might ask, well, what is step 3? Step 3 is the leaving group leaves. So if the leaving group is one of these halogens, the chlorine groups, who would make it leave? Well, the nucleophilic thing, the thing that is the most negatively charged, is going to use its electrons to push it off. So we go 2 in, 2 out. We eject that chlorine minus. So now we draw everything except for the chlorine. Everything else stays the exact same. So we only have 1 chlorine left attached to the sulfur. The other chlorine is negatively charged and it is now nucleophilic and it's on the hunt. It is a night owl and now it's looking for its food. And its food is going to be this carbon. Why? Well, this oxygen right here with the positive charge is super unhappy. It's like, oh my gosh, give me back my electrons right now, okay? So its electrons exist in this bond. So to get them back, the chlorine has to attack this carbon. 2 in, and then these 2 electrons go 2 up back onto that oxygen. So now drawing the next intermediate. Everything stays the same, so I'm actually going to do a nice copy and paste. Except for this pi bond is no longer there, so I'm going to erase it. And there is now a single bond from the chlorine to the thing it attacked, so the atom it attacked, which was this pink carbon. And now the oxygen is no longer positively charged because it got those 2 green electrons back. So its formal charge is now neutral. So if the objective is to make something like this, what do I have to do? Well, there needs to be a pi bond there, and this whole thing's gotta leave, right? One way to do this is to say, okay, what if these 2 electrons went 2 over, and we just said, you know what, leaving group, you're just gonna leave. What do we get? Well, we get that pi bond, right? That's good, that's what we want. So now we have a pi bond O. The oxygen still has that hydrogen though, and now it's positively charged, which is a problem, but usually when there's a proton problem, like an atom has a proton and it's positively charged, we can fix this problem very easily, okay? So I'm not too worried about it. And the chlorine is there. And what we got was an O minus attached to the sulfur, double bond O, and to this other chlorine. And since a chlorine is a good leaving group, what then happens is these 2 electrons say, you know what? 2 over, 2 out. And they kick off the chlorine. And what do we get? We get SO2. And this is one of the byproducts of this reaction. So we get SO2. And all we have left is a chlorine minus and an oxygen that is very unhappy. So how could we make that oxygen happy? Well, we need to give it back some electrons, right? Well, we can do this if the chlorine attacks the hydrogen, 2 in, and the hydrogen gives its 2 electrons, well, the 2 electrons in that bond, back to that oxygen. And then we get our final product. We get R to a carbon, double bonded to an O, and then a chlorine. Bada bing, bada boom. And then our byproducts are SO2 and HCl. All right, so here is the entire mechanism, step by step, for the formation of the acyl chloride. So everything we just went over. So now we've got the acyl chloride. Yay! But now let's say we want to get rid of it. All you got to do is toss in water. Where water is a really good nucleophile. Why? Well, it has lone pairs and it is small. So what can it do? Well, it can attack stuff that's delta plus, such as this pink carbon. 2 in, pi bond breaks, 2 up. Oh, look, we get a very similar intermediate where we get this O minus. The nucleophile is now attached to the carbon it attacked. And the leaving group is still there. So we have our intermediate. Now what happens whenever you have 2 atoms that are charged, where one is positive and one is negative within one structure, a proton transfer occurs. So the atom that is positively charged will lose a proton, and the atom that is negatively charged is going to gain a proton. And in that process, the negative one becomes neutral, and the positive one also becomes neutral. That is all. Now, the leaving group leaves via 2 in, 2 out. And very close to being back at where we want to be, which is the carboxylic acid. And we pretty much have it. The only problem is one of those oxygens needs to lose a hydrogen. Well, since we expelled a chlorine minus, we now know the deal. We know what happens, right? The chlorine goes and attacks that hydrogen via 2 in, and the 2 electrons in the OH bond flick up onto the oxygen. 2 up. We get HCl, and we also get our carboxylic acid. There we go. That's hydrolysis of an acyl chloride, going from the acyl chloride back to the carboxylic acid. What I want you to notice is that pretty much every mechanism with a carbonyl carbon involves 3 steps. Step 1, LG stands for leaving group. Step 1 is always this nucleophilic attack. And the second thing that happens is we get an oxygen that is negatively charged. And this is after the nucleophilic attack. And then step 3 is generally that the leaving group leaves. And then we get the formation of R double bond O is retained, but something else is attached to that carbon center. And then anywhere along this chain of events, a proton transfer could happen at any stage. It will not affect the overall sequence of nucleophilic attack, intermediate where something is negatively charged, a pi bond broke, and then step 3, a leaving group leaves. And then we always repeat this cycle. Nucleophilic attack, some intermediate, leaving group leaves. And then anywhere along the way, a proton transfer could occur. And that's pretty much it. I hope this video was helpful. I hope you have a great night. I hope your studying is going well. And yeah, good luck on everybody's next midterm or final. Please make sure to leave a like, comment, save, and subscribe to my channel if you like my content and you find it helpful. Have a great night. Bye.